piece is called handle body. So a handle body is this thing that you see here. So it's what you get by taking a graph in three-dimensional space and thickening it up. So it's that three-dimensional object bounded by that surface. We have two of them here, and we're going to glue them together along the boundaries, and we'll get some closed three-manifold, which is kind of schematically shown on top. And so you can also do the opposite. You can start with a three-manifold and look for surfaces where if you cut the three-manifold along that surface, you get the handle bodies. So those are the Heegaard splittings of that three-manifold. And so what I'm going to be interested in, and what I'm going to talk about, is trying to understand the different Heegaard splittings of a three-manifold. And in particular, I want to talk about how this is related to the hyperbolic geometry, the large-scale geometry of different three-manifolds. So here's our first example. So we have a two-bridge knot, and we're going to take the complement of that knot, or we could also think of this as doing a kind of complicated Dane surgery on that knot. So what you see there, you need to think of that as being, well, either a complement or some kind of, in this case, hyperbolic three-manifold that we get by the surgery. And on the right, we have this blue surface. So you can see that we started by taking a torus that kind of follows the knot around. So if we were to do a Dane filling or Dane surgery on that knot, that would still bound a solid torus because we're just removing the core of a solid torus and putting it back in. But then we added this tube at the top, and so what the tube at the top does is it basically adds a handle to our solid torus. So yes?
I don't know whether you're being inefficient on purpose, but I think there's a theorem that says that any two-bridge knot can be given an alternating presentation, and yours isn't.
Oh, yeah, so I'm not being inefficient on purpose, but I probably was a little lazy, yeah. That's a good point, yeah, so let's pretend that those, I think we switched those two crossings.
No, there's one up above there too.
So yeah, so let's think of this as a schematic diagram. That's a good point. Yeah, well, you'll see that if I make this change for future talks, I'm gonna have to make changes throughout the rest of. Well, anyways, yeah, so let's pretend you didn't ask that question. Okay, so on the inside we have a solid torus with a handle attached to it. So that's a genus 2 handle body. On the outside we have what still looks like a knot complement, right? This looks it doesn't look like it should be a handle body on the outside. This is in the 3 sphere, so it still looks knotted, but it turns out that well, here's what we can do. So we're starting off with, we're just looking at the outside, so I've removed the original knot. So we're starting off with the original surface, and at the top we're going to kind of pinch it together, so we kind of make what looks like a clasp here. And then we can undo that clasp by twisting, so we just twist those two, kind of grab it and twist, and we get this second piece here, right? So the complement of this surface, the outside of it, is still the same as before, because all we're doing is isotoping the surface around in the 3 sphere. And then we can do it again. We can get rid of another middle crossing. And then we have a crossing on the right that we can undo by taking the two right strands and undoing them. And then we can kind of work our way down and get rid of those middle crossings and that final right crossing. And I guess, now here, maybe your question is more significant, because it's possible that we can only do this because I do the knot in an inefficient way. But it turns out that actually, even if I had done the crossings right, so it was a minimal diagram, you could still do this. You can see that I'm not using that fact anymore. We just sort of go through. There's a simple algorithm for unknotting it. So no matter which braid I pick to produce that two-bridge knot, that tube that we added would still give us a Heegaard surface. So the outside here is now an unknotted surface. So you can see the outside, if we kind of cover up those two holes, we just have a ball on the outside. And then when we uncover the two holes, that's basically we're just kind of drilling through. So we're adding handles to the outside, and that gives us another genus 2 handle body. So is that okay? So this is a genus 2 Heegaard surface for the complement of this two-bridge knot, or for what we get by doing a complicated Dane filling on it. Now, when I added this tube, I added it at the top, right? But I also could have added it at the bottom, and that would have given us a different surface. So here are, and for some reason the slide is shifted up. I'm not completely sure why, but so it says two different Heegaard surfaces. So adding the tube at the bottom for the same reason, again, we could go up and undo all our crossings, and the complement is still going to be a genus 2 handle body, and so that gives us a second Heegaard surface for the same knot complement. So this three-manifold has 2 Heegaard surfaces, and actually there's 4 others. There's 4 other ways of attaching tubes that will give you Heegaard surfaces as well, and it turns out, so it turns out that if you kind of pick your braid to be complicated enough, those up to isotopy will actually be 6 distinct surfaces. So this three-manifold has 6 distinct Heegaard surfaces. Now for any three-manifold, we can always, if we have one Heegaard surface, we can always get a new surface by what's called stabilization. So we have our original Heegaard splitting, we take a little patch up here on the left. I guess there's nothing to point with. So we have our little patch up on the top left. We add a little trivial handle, like on the right, and that gives us a new surface. And you can see that for one of the handle bodies, all we've done is we've just added another handle to it. So we go from genus 2 handle body to genus 3 handle body. Then because that tube that we added is unknotted, for the other handle body, we're just drilling through it. And so again, we just get a new genus 3 handle body. So this gives us a new Heegaard surface of genus 1 greater than the previous one.
Just
And
there's
so-
a stick in the corner if you want it.
What's that?
In the corner, there's a stick if you want it.
Oh, there it is. Okay, well, I'll have it here in case I need it. It's probably, I think that was probably bad to point that out, because I think I'm more dangerous.
I have a question.
Yes.
Could you explain the progression of that green circle on the top? That's unfair.
You mean the red and the green circle, or the?
Yeah, especially the green.
Yeah. So that green circle bounds a disk on the outside, and the red circle bounds a disk on the inside.
So you like show like the
Yeah.
goes through the.
So the one on the left and the right are different.
Yeah,
Yeah, right.
The
So-
blue thing on the right is the light thing on top, basically. Is the
Right.
outside.
Yeah. So this, I guess I don't need this. So this handle body here is on the outside, so that's above. So the original handle body was above the little blue patch. So then when we did this, we drilled through, and you can see that the place where we drilled through, the kind of core of that tube is this is the disc bounded by that green curve. So we're kind of drilling along that. Sorry. I'm sorry. I think we're sort of drilling along that green curve in the same way that this tunnel here kind of goes around it. So the disc that's bounded by this green curve here is actually on the inside of this handle body. Right. So because we can always find a new Heegaard surface by stabilizing, we're usually interested in unstabilized Heegaard surfaces. So ones that you can't remove any handles from to get a lower genus Heegaard splitting. So our Heegaard splittings here, these are genus 2, and if we could stabilize them, that is, if it was a stabilization of a genus 1 Heegaard splitting, then we would have a knot with the genus 1 Heegaard splitting, which it turns out has to be the unknot. So we know that these are unstabilized. Okay. So the question is, what are all the unstabilized Heegaard splittings for a three-manifold? And so there are a number of three-manifolds where this has been answered for. So I won't go through the list, but these are, I think I've got all the names up there that should be. So notice, so we've got the three-sphere, the three torus, lens spaces, hyperfibered spaces. So those are actually all hyperfibered spaces. And then we have for two-bridge knot complements. So Morimoto and Sakuma showed that those 6 tunnels that I mentioned, the 2 that I showed you and the 4 additional ones, they showed that those are all distinct for sufficiently complicated braid. And then Tsuyoshi Kobayashi showed that there aren't any other Heegaard splittings. So those two-bridge knot complements are the only hyperbolic three-manifolds on this list. Everything else is a hyperfibered space. And so you might ask, why are hyperbolic three-manifolds so hard? Well, I mean, that's kind of the whole point of hyperbolic three-manifold, is that they're more complicated than hyperfibered spaces. So how do we understand, how can we understand Heegaard splittings of hyperbolic three-manifolds? And so to do this, we're going to have to introduce the curve complex. So again, Saul gave us the definition of the curve complex, and so I don't know if I should spend too much time on this, but just a quick refresher. So vertices are essential simple closed curves, so I'm not looking at arcs at this point, just loops. And we connect 2 loops, or we connect 2 vertices by an edge if the two loops are disjoint. So we have the blue loop here is disjoint from the red, so we have an edge between them, but the red and the purple intersect each other, so they don't have an edge between them. And then, as Saul alluded to, you can fill in higher dimensional faces, in this case triangles, whenever you have three vertices where the loops are all disjoint. So is that okay? Okay. So once we have the curve complex, we get to draw one of these diagrams that Saul alluded to, where we pretend that the curve complex is a hyperbolic space. So it's a Poincare disk model for the hyperbolic plane. We're going to pretend it is. And then we now have this collection of loops. So for each handle body, we have a set of loops that bound disks. So this is for a fixed Heegaard splitting, or rather the surface is a Heegaard surface when we look at its curve complex. So we have a bunch of loops that bound disks in one handle body, and so that gives us some set in the curve complex. And then we have a bunch of disks that bound, or a bunch of loops that bound disks in the other handle body, and that gives us another set. And then the Hempel distance is just the distance between those two sets. So it's the minimal length, so the minimal number of edges from any vertex in the blue set to any vertex in the pink set, which is supposed to be red. But so is that okay? So this is the distance of Heegaard splitting. And right, so Saul said that these jagged curves are usually quasi-geodesics. In this case, they're not quasi-geodesics. They're actually larger sets. They're not one-dimensional, but they are quasi-convex. And so this is another theorem of Riemann-Minsky. So for any Heegaard splitting, we have some notion of distance, which so it's a combinatorial definition, right? This has something to do with the curve complex. And it turns out that it also has to do, it turns out it also has to do with topology, but I'll get to that in a second. So the question is, can this distance be as large as you want? And so it turns out it can. And the reason is that we have a pseudo-Nosov homeomorphism acting on the surface. This takes the curve complex to itself, right? Any self-homeomorphism of the surface takes every loop to a new loop, and two disjoint loops get sent to two disjoint loops. So this gives us some map from the curve complex to itself. And what Thurston showed is if you have, if it's not finite order and if it doesn't fix any loops, then it's what's called pseudo-Nosov, which means that it acts like a hyperbolic isometry in hyperbolic space. So it basically, there's some quasi-geodesic in the curve complex that this map kind of translates everything along. And so there are two endpoints of this quasi-geodesic, which are the stable and unstable emanations of the pseudo-Nosov. So if you don't know what a pseudo-Nosov is, don't worry about it too much. I won't refer to it too much. But the idea is we have these maps of the curve complex that kind of shift everything by translation along you can think of it as a geodesic. So now if we start off with a Heegaard splitting, so we fix some Heegaard splitting, and then for some three-manifold, we can cut the three-manifold along that Heegaard surface, and then so we have some map from the boundary of one handle body to the other, which would give us back that three-manifold. We can now compose that with our pseudo-Nosov, and that'll give us a new three-manifold with a new Heegaard splitting. And when we compose with the pseudo-Nosov, what that's going to do is it's going to take our original handle body set and translate it along this, right? Because we're just applying the pseudo-Nosov to the surface, so it's gonna it ends up acting on the curve complex. And so if you pick that pseudo-Nosov correctly, and Hempel tells you how to do this, though using an idea that goes back to Tsuyoshi Kobayashi, but Kobayashi did this before the curve complex was well known, so he did it in other language, so Hempel gets his name up there. So it actually pushes the handle body away. So it pushes the blue handle body away from the pink handle body in the curve complex, and so we can make this distance as high as we want it. So in this way, so again, each time for each n, we get a new three-manifold with a new Heegaard splitting, and the distances of these will be arbitrarily high. So the distance does actually mean something in the sense that it's not always 2 or something like that. But now, what does it mean topologically, right? It's unclear from this what that should mean. And so here's the first hint that this actually does have a topological meaning. So Hartshorn, again, using ideas that go back to Kobayashi, showed that if you have a three-manifold with a high-distance Heegaard splitting, then any incompressible surface in that three-manifold has to have genus bounded below in terms of that distance. The genus is at least half of the distance of the Heegaard surface. So somehow a high distance Heegaard surface controls the incompressible surfaces in the three-manifold. So that's maybe a little bit surprising. And then Schalremann-Tomova extended this idea a little bit farther, and they showed that a high distance Heegaard splitting not only does it control incompressible surfaces, it also controls other Heegaard surfaces. So they showed that if you have a high distance Heegaard splitting, then any other Heegaard surface in that three-manifold either has high distance or is the result of stabilizing the original one. So any other unstabilized Heegaard surface in that three-manifold has to have genus at least half the distance. Okay? So somehow the distance of a Heegaard surface is also controlling other Heegaard surfaces. Now notice I have genus less than in bold. So that bothered me for a number of years because, well, I guess the question is, if you have a high enough distance Heegaard surface, will you eventually get rid of all other unstabilized Heegaard surfaces? Does that make sense? So somehow you would expect that kind of, well, at least at the time I suspected that a generic three-manifold should only have a single unstabilized Heegaard surface. And so maybe one way you can get those manifolds is picking a really high distance Heegaard splitting, and then not only would you get rid of low distance Heegaard surfaces, but you would get rid of all of them. And it turned out I was wrong. So the theorem that I'm going to talk about today, well, two theorems. So first, Hartshorne's bound is sharp. That is, there are Heegaard splittings where you also have a low genus incompressible surface whose genus is exactly equal to the bound that Hartshorne gives you. And second, so for any appropriately chosen integers, you can find a three-manifold that has both a high distance Heegaard splitting and a second unstabilized Heegaard splitting whose genus is slightly larger than the bound that Schalremann-Tomova gives you, but it's still unstabilized. In case I told you. So no matter how high you force the distance to be, you can still get other unstabilized Heegaard splittings. Okay, so again, I haven't given you much reason to be either surprised or not surprised at this theorem. So far, everything, I've told you there's some topological connection, but I haven't really told you what that connection is. And it turns out that the reason or the way that you should think about these and the way that you should understand them and either be surprised or not surprised by this is in terms of the geometry, right? So Thurston's program tells us that the topology of a three-manifold is intimately connected to its geometry. And so whenever you have a three-manifold, a hyperbolic three-manifold, you also have a geometric structure on it. And it turns out that in some sense that it's that geometric structure that's causing this theorem to be true, and Schalremann-Tomova and the Hartshorne theorem are all somehow more reflective of the geometry. So that's for the rest of the talk. I'm going to explain how that hyperbolic geometry plays into these theorems. So let's start off with a simple example. So we can take a surface bundle. So we take a surface, cross an interval. We pick, again, usually pseudo-Nosov map from the surface to itself, and we glue surface cross 0 to surface cross 1 by this pseudo-Nosov map, by this phi. So we get some closed three-manifold. And so Thurston proved, although never wrote it down, but one of these theorems that he proved and never wrote down was that if this glued map is pseudo-Nosov, then this resulting surface bundle would be hyperbolic. And we don't necessarily know much about its hyperbolic structure, although there's been a lot of work done trying to understand exactly what that hyperbolic structure is. But we at least know as a first step that it is hyperbolic. Now, when we were doing the gluing, right, we were taking high powers of pseudo-Nosov maps. So the question is, what happens when you take a high power of this monodromy, the map that we use to glue the top to the bottom? Well, then, if we replace that gluing map by a power of itself, then that corresponds to taking a cyclic cover of our surface bundle. So in other words, we're taking our original surface cross interval, and we're taking 3 copies of it, and then gluing the top to the bottom, now by this power of the monodrome. And since this is since we have a covering map here, hyperbolic metrics lift under covering maps. So the hyperbolic metric on this new three-manifold is going to be basically 3 copies of the original hyperbolic structure on the original one, just kind of stacked on top of each other. So we don't know, again, we don't know what that original one is, but we kind of know that as we take higher and higher powers, we're just getting copies of it over and over again. So there's somehow, in the coarse picture, in the limit, we can kind of see what's happening here. So what about with Heegaard splittings? So remember, what we did was we took a Heegaard splitting, we cut it along the Heegaard surface, and then we glued it back by a power of this of our pseudo-Nosov map. So you can think of that as taking your hyperbolic three-manifold, take any copy of the Heegaard surface, cut along it, and we get these two handle bodies which have some kind of geometric structure, though probably not very nice. And then we can take our surface bundle, cut it open, so we have a hyperbolic structure on surface across, so say the interval from 0 to 3. Now we can glue these all together. We're going to get something that's really awful and ugly. And again, it'll have kind of locally hyperbolic structure, but globally it's not going to look like much of anything. But then what we can do is we can take higher and higher powers of n, right? And so when we do that, we know what's happening to the middle piece, right? We're just getting more and more copies of our hyperbolic, of our original hyperbolic fin. And then at the end we have these handle bodies, which are awful and ugly, but we glue them on anyway. And we get this sort of sequence of three manifolds where we know what the hyperbolic structure in the middle is. Try again. We know what the structure along here is, and then at the ends, we kind of don't have much control over what happens. But that's okay because as n goes to infinity, most of the three manifold is in the middle, right? Most of the volume is in the middle. And in fact, what Nematzi and Soto showed is that as n gets bigger, you can actually pick a pretty nice metric on these. So it's epsilon pinched hyperbolic curvature. So they're able to very explicitly construct this metric, and it's close enough to hyperbolic metric that when epsilon gets small enough, you know that it's basically the hyperbolic structure. So they give you a very nice picture of these three manifolds, and it basically looks like this, where you have this long, thin neck, which is again all these copies of the surface bundle or the fundamental domain of the surface bundle, and then kind of capped off by something else. Okay, so is that okay? So this gives us a kind of coarse picture of what three manifolds with high distance Heegaard splittings look like. Okay, so So now we get some technical lemmas. So if you have an incompressible surface, it's going to intersect every cross section of this long thin neck, right? So we have all these cross sections, copies of the Heegaard surface, which come from the surface bundle structure, and every incompressible surface. So that's the green surface, and then every incompressible surface looks like this blue surface, where there may be some trivial loops, although there are ways to get rid of those, but there has to be at least one essential loop. Okay, so this is a piece of that cross section, and the incompressible surface kind of wiggling through that. So now we know two other things. So we can choose this incompressible surface to be harmonic, which means that we have a bound on sectional curvature. And then, so we now, and that tells us that the area of this incompressible surface is going to be proportional to its genus. Now we go back and say, well, we know that this loop here is essential. And because of the way we chose the cross sections, we just see the same surfaces over and over again, right? Because we saw it by unwrapping the surface bundle. So we see the same surfaces over and over again. So we have a bound on the injectivity radius, right? So in other words, we know that there's some value, say, I don't know, lambda, is that a good injectivity radius, where any essential loop has length at least lambda as we go across this cross section. Now, if we go through the areas, it's going to be the integral of all those lengths. And so that means that if n is high enough and we have a really long middle piece, then when we integrate, we have a lower bound on the length, and we're integrating those lengths across the whole thing, and the area is going to be large. I won't try to use that again, I promise. Maybe just one more time. So to sum up, we have a lower bound on lengths. Oh, I really want to. Just one more time, I promise. So the lengths are bounded as we go across. We're integrating them all together to get the area. This thing is really long, So that means that the area has to be large, and then Gauss-Bonnet and the fact that it's a harmonic surface tell us that the large area implies large genus. And so we can see that in other words, any surface that kind of cuts along the long way across here has to have high genus. Every incompressible surface has to do that. And so that's kind of a geometric version of Hartshorne's theorem. If we have this long, skinny hyperbolic metric, then all incompressible surfaces are high genus. Now, Hartshorne proved this completely topologically. He didn't say anything about the hyperbolic metric on this three-manifold. So how did he do it? Well, he again, so this is again a trick that goes back to Tsuyoshi Kobayashi, but he noted that if you have, so every saddle in your surface, so every pair of pants, so again, as you're going through these parallel surfaces, whenever you have a saddle, the two loops before or after are disjoint from the new loop. That comes, well, so I guess we're going down. The two loops before the saddle are disjoint from the loop after the saddle. Of course, this is schematic, so you can't exactly see that, but it's not too hard to show that as you go through, each time you go through a saddle, the loops after the saddle are disjoint from the loops before the saddle. And then you note that the beginning and ending loops, because so this sort of starts at a really small handle body that's just a regular neighborhood of the graph. So the starting loop has to bound the disk in this handle body. The ending loop has to bound the disk in this handle body. And then as you go through, each saddle in the surface corresponds to a step in the curve complex, or at most a step in the curve complex, which means that as you sort of sweep across this surface, you get a path in the curve complex that goes from some disk in this handle body to some disk in this handle body. So that's a kind of a topological analog. So instead of integrating all these lengths and using the lower bound on injectivity radius, we're adding together all these saddles. So the number of saddles is at most the length, and then you have to add one edge at the beginning and end for various reasons. So the length of this path is at most the number of saddles in the surface plus 2, which is exactly twice the genus. So saddle is basically a pair of pants. Okay, so again, this is a topological analog of that geometric picture.
What in your picture is sigma?
So sigma is, well, there's a lot of sigmas. So there's sigma, each of these cross sections is a copy of sigma.
So you're thinking of like this is the covering, and downstairs they're all just sigma, and you're just moving from one curve to another.
Yeah,
and that's what the line across the top is.
Right. Yeah. So we have. So this is a product, right? So we can project any loop in there, or any loop in a horizontal surface. We can project down to the base surface. So at each cross section we get a loop, and we're kind of projecting that into sigma. Does that make sense? Yeah. So this vertex here is the loop in this cross section. So any other questions? So Schalremann-Tomova proved their theorem using basically the same method. So again, it's a topological proof, and what they do is they show that if you have a second Heegaard surface that's unstabilized, then you can isotope it so it has the same type of structure as the incompressible surface. In particular, there's going to be an essential loop at every step along this way, so again, you get a path in the curve complex from some disk on one side to some disk on the other. So this is somehow the unstabilized Heegaard surfaces in certain situations behave a lot like incompressible surfaces, and so that's why we get the same theorem in both cases. Okay, so now we have a geometric interpretation of this topological theorem. But what does this have to do? So this tells us why there shouldn't be any low distance Heegaard splittings. But now the question is, how do we talk about higher genus Heegaard splittings? How do we use these methods to talk about in particular, distinguishing Heegaard splittings? So here we use an idea that came up in work by Haas, Thompson, and Thurston. So they were the ones who introduced the geometric perspective on this. And so here's the idea: if you have a Heegaard surface, and again, we're coloring the handle body so we can distinguish between the two. So here the blue handle body is on the inside, the pink's on the outside. And I'm going to say that a Heegaard surface is flippable if you can isotope that surface within the three-manifold so that it comes back to where it was at the end of the isotopy, but the two handle bodies are interchanged. Okay, so we're kind of flipping it over. So you can, you may have seen how to do this for a sphere in the three-sphere, or two-sphere in the three-sphere, which is a unit zero Heegaard splitting, where you kind of take the top and you pull it over the point at infinity and down. And so maybe you've seen how you can do this with a torus in the three-sphere. I don't know. It is an exercise, maybe not. Anyways, it's a fun exercise to try and convince yourself that you can do that. But is that clear? So we're taking one Heegaard surface, so that these are both the same Heegaard surface, but the inside is the outside here and vice versa. Okay, so now we're talking about isotopies of Heegaard surfaces. So what Huss, Thompson, and Thurston showed is that if you have a high distance Heegaard splitting, it's not flippable. And actually they showed something stronger. They showed that to get a flippable Heegaard splitting, you have to stabilize it enough times to double its genus. But basically, here's why. So again, schematically, right, we want to turn this picture into this picture, right? Same Heegaard surface, but with the colors interchanged. And it turns out you can do this in a way where the volumes are equal at every given point. So the blue handle body always has the same volume as the pink handle body. And so you can kind of see how the only way we would expect to be able to do that, and again, the picture, of course, is oversimplified, but we'll pretend right, the only way to do that is to kind of stretch it the long way across the three-manifold. Right? That's the only way that we can flip this over while keeping the volumes equal. Is that okay? So I guess you're going to have to take my word for that. But the point is that somewhere in the middle, right, we get a picture where the surface cuts the long way across the three-manifold. So this is another schematic for the picture here, right? So somewhere in the middle of our isotopy, we get this guy. And then again, either geometrically, Huss, Thompson, Thurston do this by adding up the cross sections to get a high area. But you can also do this topologically if you can find that middle surface and get a high distance on the curve complex.
Do they talk about high distance splittings or just
No.
by this construction?
Yeah, that's right. Yeah, so that's right. So they do it geometrically. So they're only talking about three-manifolds where you have a sufficiently high power to supernovae. Right. But you can translate the basic idea into a topological. So that's what I did.
And you did it.
Yeah. So when I say you, I mean me.
Yeah.
Okay. So right. So now we see that distance can control isotopes, right? So in particular, it can tell us, maybe it can tell us when two Heegaard splittings are different, right? And the problem here, of course, is that we know that if the distance of the Heegaard splitting is high enough, then of course we know there are no other Heegaard splittings, so there's no other Heegaard splittings to control isotopies of. So what we have to do is to find ways to kind of weaken the constraints just enough that we can still say something, but so that there will be other Heegaard splittings around. So one way to do that is what's called the three-handle body decomposition. So here I've drawn both the topological and the geometric interpretation. So what we do is we take three handle bodies, that's why it's called the three-handle body decomposition. We draw a separating loop on each handle body, and these loops are very simple because of fly here. I don't know, you guys smart. So I keep seeing this little black or little gray dot go across. Anyways, so these are simple loops, but really these are going to be high distance. So in the curve complex for each handle body, we want this separating loop to actually be high distance from every disk in the handle body set. And then we're going to glue subsurfaces together kind of in a cycle. So the left yellow to left pink, right pink to left blue, and right blue to right yellow. And again, we do this so that the loops separating the subsurface from each other are high distance. And it turns out that what we get, well, what we would expect it to be geometrically, and the folks who study the hyperbolic structures of these types of constructions kind of agree, at least in principle, this should be the case. So what we get is a hyperbolic structure that looks kind of like a tripod. So each of these is the handle body, right, which is kind of this long, thin surface cross interval with the handle body attached at the end. and then we have this juncture in the middle where they all come together, kind of. And so the middle of this juncture here is this loop that we get by gluing these three loops together. Okay. So this is a three-manifold. Now you can say, well, what are its Heegaard splittings? Well, so here's what we're going to do. We're going to take some of the handle bodies, and we're going to do. You're going to see this picture in the next slide. This is a schematic. And what that means is that we've taken two handle bodies. So we've taken, so here the top is the boundary of one handle body, the bottom is the boundary of the other handle body, and we're going to attach them by a tube. So this Heegaard surface is the boundaries of two handle bodies with a tube between them. Now when you do that, it turns out the inside here is a surface with boundary crossing interval, which is not too hard to show as a handle body. And then that's kind of attached to another handle body. And then, well, what we have up here is two handle bodies glued together by a tube, so that's another handle body. So when we do this, so again, I'm just going to show you the schematic. We have three Heegaard surfaces. So here's one. So we have this handle body and this handle body with a tube between them. And then we have this surface with boundary crossing interval that's glued to another handle body, and it turns out it's glued in a way that the whole thing is a handle body. So this gives us a Heegaard splitting of this tripod manifold, where the Heegaard surface is this thing in the middle. Right? But we had a choice when we did this, right? We picked the bottom and the left handle bodies to combine, right? We could have picked the upper and the right handle bodies, or the upper and the left, and so we get three different Heegaard surfaces. So this is three different Heegaard surfaces with the same three-manifold. Now why?
Can I ask a question?
Yes, go ahead.
So why is, let's say in the lower left, why is the blue thing a handle body? I mean, you're attaching this surface cross I
Right.
to, or surface with boundary cross I, you're attaching to some really complicated curve,
Right.
right?
Yeah, so
Because
so
you chose the meeting curve to be high distance from it. So why is that still a handle body?
So that curve is high distance in this handle body, but it's actually in this handle body. It's very simple. So this thing here, that little so that's a surface cross interval where the surface has two boundary loops. One boundary loop is along this tube, and the other boundary loop is right, because that's sort of it's the original subsurface with a puncture. So it's the boundary of that original subsurface. So it turns out that that loop that you're gluing across is primitive in that handle body. And so since we're only gluing along one primitive loop, we can get a handle body. It's a good question.
Oh, I see. So the point is that the thing they're glued together, it's simple in the kind of small additional thing.
That's right.
It's complicated on the other side, but it's simple on the other thing. So
Exactly.
you're going
right.
along a primitive thing. So okay.
Yeah, so this annulus here is very complicated in this handle body, but it's primitive in this handle body. And that's all you need to get a new handle body. So, So we get three Heegaard splittings, and you can show that they're distinct, but let me tell you why you expect them to be distinct. So the reason is to get from, say, this picture to this picture, right, what we have to do is we have to pull the Heegaard surface, we somehow have to get it over this handle body, or we have to move it from one side of this handle body here to the other, right? And so to do that, we might expect, and it turns out it's essentially true, that we would have to do something like this, right? We'd have to pull it the long way along that handle body. So we have this long leg that we want to pull the Heegaard surface over, and the geometric picture tells us that we would expect to be forced to have really high area, because there's going to be somewhere in the middle where it kind of comes out the long way here. And again, you can also prove topologically that this also happens, that you can sort of get a path in the curve complex from this loop here to a disk out here that tells you that your separating loop that you used to kind of make that leg was low distance, or that its distance is less than the genus of that Heegaard surface. So geometrically, we would expect these three to be distinct, and it turns out that they are. So we can see now, we kind of get a hint of how you can use the geometry of a hyperbolic three-manifold. If you understand its geometry, we can use that geometry to try and understand what the Heegaard splitting should be. But this is still doesn't give us our theorem, because it turns out these three Heegaard splittings all have distance 2. And I won't Well, again, another fun exercise is to show that they all have distance too. I won't, I'll just leave that as an exercise. So this doesn't give us what we want, and somehow the problem is we've released some control, right? We've loosened things up enough to get 3 Heegaard splittings, but we haven't loosened them up enough to get high distance Heegaard splittings. So to do that, we're going to need to talk about subsurface projection. So now we're going to use the arc in curve complex, which Saul also talked about. So it's, again, this is like the curve complex, except that we now have properly embedded arcs, properly embedded essential arcs as well. And so, you know, two arcs or a loop and an arc are, if they're disjointed, we put an edge between them and all that fun stuff. So if we have a subsurface of our Heegaard surface, so this purple subsurface, can you guys see that purple? I don't know, I kind of randomly pick these colors, so I have no idea how good they work. But so if we have 2 loops in the surface, and we have a subsurface, we can take the intersection of those loops with the surface and we get some arcs. And in general, you may have more than one arc. Here, they happen to be 1 arc each, but so that there's some details that I'm leaving out. But we get a projection. So this loop, these 2 vertices in the curved complex of this surface give us vertices in the arc and curve complex for the subsurface. And you can see that these 2 arcs are high distance in that subsurface. Or, I mean, I could have, I don't know if they actually are high distance, but in theory, I could have made them as high distance as I wanted. But the loops are still low distance, right? There's this loop out here that's disjoint from both of them. So the curve complex, the red and the blue, are distance 1. In the purple subsurface, they're distance, I don't know what that is. I guess the blue, I didn't tell you how to connect up to the back. So they're distance, whatever you want them to be. So so here's a lemma, which I don't know if this is explicitly stated in the literature anywhere, but it's certainly implicit in a lot of work, certainly Mazur and Minsky, and a lot of what Saul did. And Ivanov may have used this. So Ivanov introduced the idea of subsurface projection. So the lemma says that if you have 2 loops that are high distance in the subsurface, but they're low distance in the overall curve complex, then any short path between them has to include a loop that goes out of the subsurface. So, and this is actually, I mean, once you see the proof, it's very natural. The idea is that if you had a path from red to blue that always intersected the subsurface, then those projections, you intersect those the intermediate loops with the subsurface, and you'll get a bunch of arcs that will give you a path in the curve in the arc and curve complex for the subsurface. And that would be a contradiction to the fact that they're high distance. So that means at some point the loop has to leave the subsurface, so the projection is not well defined. Okay, so having a high distance subsurface, so in the curve complex, that means that any path kind of has to miss the subsurface. Or in other words, any path between these loops sees the subsurface, and it sees it and it gets out of the way of it, right? It has to kind of take that subsurface into account somehow. So there's also a 3-dimensional version of this lemma. So this is joint work with Yair Minsky and Yoav Mariah. We showed that if you have a, so here this green arc is supposed to be a Heegaard surface that's low distance, so the Hempel distance of that Heegaard surface is low. But if you look at the subsurface projections, you look at the intersection of all the compressing disks in either handle body with some subsurface, and then you compare their distance in that subsurface in the arc and curve complex. If that's high, then any other Heegaard surface for this 3-manifold, it can do whatever it wants in general, but it has to be parallel to this subsurface. So in other words, any other Heegaard surface sees a high distance subsurface. So this is a very kind of natural generalization of Schalremann-Tomova's theorem, right? So Schalremann and Tomova say that if the whole Heegaard splitting is high distance, then any other Heegaard surface is parallel to that. This theorem says that if you just have a subsurface that's high distance, then any other Heegaard surface sees that subsurface but doesn't necessarily care about the rest of it. And so in other words, you can think of that high distance subsurface as being kind of a bubble. And that bubble should really be long and skinny, but you'll see in a second why I made it round. So somehow the geometric picture is that high distance subsurface is a big bubble of hyperbolic volume. And so in order for this blue surface, so it's a Heegaard surface, so it has to be able to get from one side of the bubble to the other. And the most efficient way to get across it is to kind of be parallel to the kind of narrow direction of the bubble. So this is a three-dimensional analog of this lemma. Okay, so again, high-distance subsurfaces correspond to hyperbolic columns. So we can use hyperbolic subsurfaces, we can use high-distance subsurfaces to create geodesics. So this is a construction that essentially goes back to Ito, John, and Kobayashi. And it also, I guess, has its roots in work of Berman and Manasco, who similarly used subsurfaces to construct geodesics. But here's the basic idea. So we start off with some loop L1, which is this blue loop here. I don't know well, I guess, so L1 is this blue loop. Then let's see. Right. So what we do is we pick a green loop that cuts off a once punctured torus containing that blue loop, and then we pick another red loop in that once punctured torus that's high distance from the blue loop in the subsurface in the arc and curve complex for this subsurface. Okay, so in other words, the red and the blue loop, they're distance 2 in the whole surface, but they're going to be high distance in this one punctured torus. And there's actually, so the red is L3. So you can see that these are distance 2, and there's lots of paths from L1 to L3, right? Because we can take any essential simple closed curve in this part of the surface, and it'll be disjoint from both. Okay, so this is it's a flexible geodesic. So then what we do, we erase the blue and the green, and we take some other loop that separates a once punctured torus containing the red, but is high distance from this green. So the original green and our new separating loop, those have to be high distance in the complement of the red. So they'll also be distance 2. And then we do the same thing. We have a once punctured torus containing this red loop, and we're going to pick some high distance loop there. And what this does, so basically what this tells us, if you look at any, say, L5, you can do this in such a way that all the loops before it, in the complement of L5, they have high distance from all the loops after it. Okay, so what we get is that in this particular path, every loop to the left of L5 has high distance from every loop to the right of it in the complement of L5. And then the lemma says that since they have, since they're high distance in the subsurface, any path from, say, L1 to L13, since those are high distance in the complement of L5, every path has to be disjoint from the complement of L5. So it actually has to have a loop disjoint from the complement of L5. So in other words, it has to have L5 somewhere in that path. So that was kind of fast. But I don't know, I guess in the interest of time, I won't try to say that again. The point is, we can use this lemma to guarantee that every geodesic from L1 to L13 goes through L5, goes through L7, and goes through L9, and so on. And so we know that every path from L1 to L13 hits all the odd ones, and then we kind of know that that's enough to guarantee that it basically follows this general geodesic. So we were using subsurface projection to guarantee that this is a geodesic. Right. And then there's a way you can then extend this, put in a handle body set on either side of this, so that that's the shortest path between the handle body sets. And I won't go into the details of that. And so what does this do? So again, for each loop in the middle here, we have a high distance subsurface, right? Each of these odd loops corresponds to a high distance subsurface in our Heegaard splitting. That's kind of how we constructed it. And we see in the two-dimensional picture in the curve complex that guarantees that this is a geodesic. So the three-dimensional analog of this is this picture here. So again, we have the sequence of high-distance subsurfaces. So that gives us the sequence of of large volume bubbles in our hyperbolic three-manifold. Okay, right? Because So this is the subsurface. So sorry, here this is the subsurface defined by L3, the subsurface defined by L5, and so on. And so each of those gives us a hyperbolic bubble, and we would expect that any other Heegaard surface would see those bubbles, right? In particular, if we have an alternate Heegaard surface, so an unstabilized Heegaard surface that's unrelated to our cross section here, it would have to see all those bubbles. It would have to read between them, right? Which on the one hand guarantees that it's high-genus, but on the other hand, we kind of want to think of it as being trapped in there, right? If we construct it in such a way that it doesn't have a subsurface parallel to this bubble, then it can't move across it in some schematic sense. So we would hope that there would be a Heegaard surface that's kind of trapped in here like that. And let's see. So in the interest of time, so I don't know if I have time to go through the topological construction carefully, but let me just show you quickly what we do. So we start off with a disk that bounds the first loop in the path, and then we have so this was a separating loop, and then we have our non-separating loop, right? That was the red loop before. So we put a pair of pants in there so that this pair of pants has two loops parallel to that one, and then the disk, you can't see it because it's behind the surface, the disk is back there. Then we attach two annuli. So again, we took that original pair of pants, pushed it into the handle body, and attached these two annuli there. And then we're going to put on another pair of pants to this time to a separating loop. So this is the separating loop bounding a once-punctured torus containing L1. And then we do the same thing. We add a vertical annulus and then go to another two copies of a non-separating loop and so on. And so basically what we're doing is for each step in this path where we have a pair of pants. And the first pair of pants is capped off with the disk. So so for each step, we're constructing the pair of pants that we would expect from basically the Hartshorne's proof. And it turns out that because these subsurfaces are high distance, you can show using, I guess, the lemma that goes back to Mazur and Schleimer, you can show that these surfaces that we're building up are incompressible within each handle body. And so in particular, if we go all the way through and we kind of put in another four-punctured sphere there, under the right conditions, we'll get an incompressible surface. And again, you can show that it's incompressible because of the high distance subsurfaces. But we don't want an incompressible, we want an incompressible surface, but once we're happy that we have the incompressible surface, then we want a Heegaard surface, right? So we have to do something to guarantee that that the surface that we construct is still a Heegaard surface, but is unstabilized. And so what we do is we put in a junction that looks like this, which I know it takes some staring to get used to it, but basically we have two vertical annuli below, two vertical above, and then we have this thing in the middle. Let me show you another picture of that, of the horizontal part of this. So it looks like this. So these are two loops. So these are two non-separating loops in a single once-punctured torus, but in this case, they intersect in a single point, which is this square here. So we have this thing. The two parallel loops here have vertical annuli coming down into them. The two parallel loops here have vertical annuli coming up into them. And so this thing, it turns out is a surface. I don't know if that's how hard it is. Some things like that just, well, I don't know how obvious it is that that's a surface. So when we do that, we get this surface here, right? So the blue thing here is a twice punctured genus 2 surface, right? Can you see that? If you thicken it up, if you take a regular neighborhood of this, it's a twice punctured genus 2 surface. So that's not the surface that we want. The surface that we want is actually what we get by adding these annuli. So when we add the vertical annuli, we get 4 boundary components instead of 2, but the same Euler characteristic, which means that this is, so when we add the annuli, the surface that we get is a 4-punctured genus 1 surface. So it looks like this. It gives us this surface, which has half the distance plus g minus 1. Let's see, and right, and so it turns out. Oh, let me just say one more thing. So we had the surface above, which was incompressible. So it turns out incompressible surfaces cut handle bodies into handle bodies. So we have two handle bodies above, two handle bodies below. Two of them meet along this green disk, and the other two meet along this other green disk. And when you glue handle bodies along disks, you get handle bodies. So that means our four handle bodies get glued together into two handle bodies that bound the surface here. And so, and then with a little more work, you can show that this is unstabilized, and its genus is half the distance plus g minus 1. And so that, so that gives us a surface which is very much the surface, or it's very close to the surface predicted by Schalremann-Tomova and Hartshorn. And it turns out with the subsurface projection machinery, you can actually show that it's unstabilized. So that's how you get the construction. So I'm out of time, so I'll end there.
Other questions, comments?
So,
Yeah.
here's a question. So your Kobayashi-esque geodesic, which is pretty long, seems to suggest schematically that you could put the complicated block in many places. Does that give you many alternate surfaces?
No, so there's one thing which I kind of glossed over, which is, so here, at the step where we put in this middle block, we want these two loops to intersect at a single point. Whereas at all the other blocks, we want them to be high distance in that one-function torus. So basically, there's one geodesic. If they're all high distance, then you'll get a compressible surface. If there's one that's where they intersect at once and the rest are high distance, then you get one Heegaard surface, which corresponds to that block. If more than one have this structure where you intersect at a single point, then all the Heegaard surfaces are stabilized, or at least weakly reducible. So I think those will actually be stabilized. So as far as I know, you can only get one alternate Heegaard surface this way. Though, I mean, there's a lot of room to play around. So I'm sure there are other constructions.
Any other questions? Let's thank Jesse again.